So this is a very simple past year question, all right, that I will discuss together with this video so you have a better understanding of the circuit. Okay, so I'm going to quickly do A first because we are going to talk about the LDR. So it says that the resistance of a LDR is approximately 500 ohm in daylight. So in daylight, the resistance of the LDR is very small. Suggest an approximate value of the LDR in darkness. So when the LDR is in very dark conditions, right, the resistance should be larger, but not larger like 550 lah. That one has not much difference, right? You need to increase it by a lot. So the suggested value that you should put, especially when it's approximate, please understand that this have to be 1 SF, a bit like your estimation question in your AS. So this resistance value should be at least 10 times greater, because then there's no meaning for you to have a larger resistance in darkness. If your larger is just a little bit more larger, might as well just put another resistor there. Okay, so the function of the LDR have to be pronounced. So this value of R can be something like 5 kilo ohm or 10 kilo ohm, 10 kilo ohm, 5 kilo ohm. The mark scheme allows R to be greater than or equal to 5 kilo ohm. All right, so I'm going to move on now to the actual circuit. Now, whenever you see a circuit like that, the first step is to breathe and don't panic, okay? Normally, the circuit you can separate into sensing, processing, and output. So I'll separate for you now, okay? Divide and conquer ma, you know? So right now, whatever that is at the input is the sensing. This is the sensing devices. Sometimes they don't even bother to draw. These are your input. Okay, so you have a few input here. When I see the input, immediately I will label. Okay, so I'll zoom in a bit for you to see. This input, this V minus is positive 2.5 volt. So the inverting input has a potential of plus 2.5 volt. Okay, important point, I'll write it here. What about this V plus or non-inverting input? Don't know because if you check this connection for V plus, let me change color. You check this connection for V plus, or it is connected here. Oh, it is connected to this thing. And what is this thing? Let us stare at it for a bit. This looks like a potential divider, right? On top here, there's this 4.5 volts, all right? And it is connected with two resistors in series. You have the 1.7 kilo ohm. And you have this LDR here. Okay, this is the symbol of a LDR. So if you're wondering where V plus is, remember this is your ground line. Your ground or 0 volt is here. Meaning every point on this line, this red color line, is 0 volt. I'm now regretting using red, but never mind. Okay. 0 volt. So this one is your ground line, 0. Everything on this line connected here is 0. So yeah, right lah. You are 0, you are 0, everyone is 0. Okay. If you want to measure V plus, we always measure from ground, right? So V plus will be the value from here to here, which also happens to be the value across the LDR, because one side is 0 ma. Right? So here to here is also your V plus. We probably need to do some ratio thing later. Okay, we put that one side first. Don't want to brain. Park one side. Okay. Next part, the center part. Study the processing unit or the processor. Here is the processor. Your processor is very beautiful. It has no feedback loop, meaning there's no connection. There's no other connection that redirects anything from the output back to the input. So this processor, first thing you notice is open loop. Very nice. Second thing you notice is your VS. This is your VS, meaning you will saturate at plus minus 9 volt. The saturation potential will be plus minus 9 volt for your V out. So I will write this here in case I forget. Okay, and side here are things that you may not have seen before, or you have. Whenever you see this kind of triangle with the arrow one, very familiar. Seen this before in AC? It looks like this. It's the diode. Got forward bias, reverse bias. We spend some time showing you the half-wave rectification. So what you need to know about this is just it only allows current to flow in one direction. This one is okay. So now you see these two diodes looking thing, they are flipped in opposite direction, meaning they will only allow current to flow based on what they want. Okay, so now we are at here, and this part, all these things here, we will call this, whatever that is connected to the output, I will label your output for you. Which color should I use? This one. So this is your V out. And your V out, anything that's connected to your V out from here to here is known as your output devices. So an example of an output devices here are LEDs. So whenever we see this symbol, this is a diode. But whenever there is an arrow pointing out like this, means that the diode will shine light. So this is a LED, light emitting diode. It is likely that you have LED lights at home. Okay, light emitting diodes. Miss, this one also got arrow. This one also got arrow. Good observation. If the arrow is pointing away from the circuit component, it means that the circuit component will shine light. If the arrow is pointing towards the circuit component, it means that the circuit component will respond to light. So when the arrow is pointing out, we will, this is only if you always confuse with the sign. Because I've seen students draw LED where the arrow point in opposite direction, and then I feel very sad because I cannot give marks. Because it's like LED that respond to light. So whenever the arrow is pointing outwards, this arrow like that, away from component, we will say that this one is emitting light. Okay, and then when you have this thing, when the arrow is pointing like this towards the component, this means that it responds to light. Okay, so here you have two LEDs. They will light up when current flow. Let's decide the direction. For the red LED, it will light up when the current flow like this. For the green LED, it will light up when the current flow like this. Oh, so now it's time to dig back this ancient knowledge from your AS. When current flow, do they flow from high potential to low potential? Low potential, high to low, low to high. If you're thinking high to low, then you are correct. So we are going to flow from high potential to low potential, but you see this bottom line now is 0. So let's consider point P. Point P to point 0 means P must be bigger than 0. And all numbers bigger than 0 have to be positive. So if this current flowing, I will say this one will flow if VP at point P is positive. Whatever positive number that is bigger than 0, the current will flow. Okay, and then for this case, if your current is going to flow from ground up, you must flow from high potential to low potential. Let's say this point here is Q. So your point Q must have lower potential than 0. Lower potential than 0 must be negative. So if this one is when the potential at point Q is negative. All right. And of course, whether point P and point Q is positive or negative depends on your output. Because the output is connected here. Ding, ding, ding. Connected like this, the output. I have a magical changing color pen. Okay, so depending on whether the output is positive or negative, the LED will light up. And one last thing, because I'm just analyzing every single thing that I can in this circuit. That would be this R. Occasionally, they will ask you, why we connect this R here? Whenever you have a resistor connected in series to an electric component, its purpose is always to protect. We must protect the LED. And why must we protect the LED? Because if the current is too big, then the LED will fry, and then you have to replace the component. So the role of R, I'll write it here at the side. The role of R is to protect the LEDs from large current. Okay? So now we know when this light turns on. This one, the red one, turns on if V out is greater than 0, positive. Okay? The green one turns on if V out is less than 0, negative, because current will flow up, flow down. And now we are ready to answer the question. So whenever you see a circuit, if you want to feel a bit safe for yourself, learn to analyze the whole thing before you start answering the question. Because now you unlock the whole question now. You can ask the question, what you want? I can do. What you want? Okay, so the operational amplifier is ideal. Resistor R are to ensure the light-emitting diodes LED do not overheat. Good job. On figure 9.1, mark the polarity of point P. Sure. Mark the polarity of P for the red LED to be emitting light. Okay, we are ready. Should P be positive or negative? And I have another one. It's the same circuit, okay? So what do you think P should be? Down here is 0 volt. Current is going to flow like this. So P should be positive. Write a big positive at point P. So current will flow from positive to 0, high to low. Okay, done. The LDR is in daylight and has a resistance of 500 ohm. Okay, LDR 500 ohm. State and explain which diode, red or green, will be emitting light. So you must state and explain. And this is 3 marks. So where is the LDR? LDR is here. This is your light dependent resistor. Because it depends on light, that's why the arrow is pointing in. Okay, and it says here that in brightness, yes, in daylight, the resistance is 500 ohm. So I'm going to label that 500 ohm first. Okay, so this is your LDR, and it was 500 ohm. I label everything first. 500 ohm in daylight. Okay. So some of you that are a bit more perceptive or a bit more like, I miss this positive 4.5 volt 从哪里来? Where is it from? Why got this one? Okay, you don't panic first. Generally, what is happening here is they will connect this part to some battery lah. Okay, there's a battery here, and it's connected to the supply. And generally, as mentioned previously before, the supply is actually connected this way so that I can maintain a 0 ground line. Okay, and because when we draw this, it becomes too messy, correct or not? You see this one also, we have to draw again. The circuit is already looking fairly complicated and headache. If we keep drawing and adding power supplies, then it's going to just give us more headache. So generally, people do not draw this. Okay, but if you want to, I draw for you lah. Okay, so normally when you do DC, our suggestion to you was start from the power supply, decide where the current flow, etc, etc, etc. But when it comes to more complicated circuits like this, a better way to, or a more easier to brain approach would be consider why every component is there, and then understand that normally we do not draw power supply or in its entirety because it will make the circuit too complicated. So what you need to know is just where the ground line is. The ground line. Your 0 volt is your reference line. This is very important. All current will return to ground. Okay? Or come from ground. your reference point. All right. And whenever I can put a potential, look, you see this 2.5 volt, this 2.5 volt, you from where? Then another battery, wow, means like that very headache. You know, also good lah. So we would prefer to not have any of this in case, it makes the circuit a bit more complicated. We just need the ground line. Okay. I am going to leave that here because right now what we actually need is to find what is the inverting and non-inverting inputs for us to decide which LED will light up. So I'm going to put this one as your inverting input, and this is 2.5 volt, right? And I will erase this because it's blocking my Zen. No lah, just blocking my drawing. So we want to find what is V plus. Previously, I have explained that V plus will be the potential difference across the LDR. So we need to find a value for this V plus when the LDR is 500. Use ratios. Okay, this V plus, if you have already watched the chapter 19 and 20 videos, we will use ratio to solve this. This is a share of 500 ohm. Consider its sibling or its partner resistor that is connected in series with it. So they are connected in series this way to the 4.5 volt. So meaning to say everything, the potential across both resistors from here all the way down here is 4.5 volt. They are sharing 4.5 volt. LDR gets a share of 500 out of 500 plus 1007, 1.7 kilo ohm. So now we're going to press our calculator to figure out what V plus is. Okay, so after pressing my friend Casio, the calculator, this is 1.02 volt. You write it to 1SF, it's just 1.0 volt. We'll just keep it to 1SF. Why? Because your V minus is also 1SF. So this is 2.5 volt, and currently the potential difference that is being compared to is 1.0 volt. Okay, which one is bigger? Which one is bigger? 2.5 is greater than 1.0 volt. So I'll just put a note here. And I say that V minus, which is 2.5, is greater than V plus. So if V minus is greater than V plus, what happens to your supply? Our V supply will be negative. Means negative what? Negative 1? Negative 2.5? No. Supply, negative 9.0 volt. So if your V supply is negative, if this is negative, then which LED will light up? We have already decided this just now in the analysis. If this is negative and this is 0, the green LED will light up. So this one, green LED will light up. So now we need to write all of these points nicely in equation, but in sentence form. Hiya, okay lah, come lah, we write together. Say and explain lah. We explain first lah. Okay, so you can say that V plus, which is the non-inverting input, and I'll bracket V plus so I never have to write the full name again, is equal to, and I will also show the working because sometimes the mark scheme will ask for the working. So I'm going to say this one is equal to 500 over 500 plus 1700 times 4.5. Okay, which is equal to 1.0 volt. Okay, and then I'll say since the inverting input V minus is equal to 2.5, positive 2.5 volt, the inverting input is greater than the non-inverting input. So, hence, the supply voltage or the output, sorry, not the supply, the output voltage, V out is equal to negative 9 volt. So because of this, the green LED emits light. And then there was this anomalous year. So because of the anomalous year, I have reformed my writing a bit. Green LED emits light. Red LED does not emit light. Of course, there was this year where you never say if the red one emit light and the other one does not emit light. It's a bit sus that they will minus your mark. So you just say the red LED does not emit light. Okay, so where are the 3 marks? 1 mark is when you talk about how the non-inverting input is 1 volt and you need to show the calculation. 1 mark. 2nd mark is when you say that the inverting input is greater than the non-inverting input, hence the output is negative 9 volt. So a logical comparison and conclusion. Because why? This is a comparator circuit. So you need to compare and conclude. So greater than is a comparison. Output is negative 9 volt is a conclusion. And your final result is your last mark. Green LED emits light. And there was this year where the students need to write red LED does not emit light. So you hampelang, just hampelang is everything. Everything just throw inside lah, okay? So this one is 1 mark. The outcome or the output devices. So relate it back to the output device. This one is 1 mark. I actually think if you can do this, it's fairly predictable. And it's not that hard to get full marks. Alright, so let's move on. The intensity of the light decreases and the LDR is in darkness. Okay, fine. The LDR is in darkness. State and explain the effect on the LEDs of this change in intensity. Okay, so they didn't specify what this new resistance of the LDR is. So, well, you can't calculate. So you need to go back to your calculation and ask yourself, what happens in darkness? I will use black pen for this. So in darkness, the resistance of LDR increase. Think of the electron, less energy to move, don't want to move. So the LDR resistance will increase. So if the LDR resistance increase, this 500 become a bigger number. So this 500 becomes a bigger number, it gets a bigger share of the potential difference 4.5 volt. So the resistance increase. The second one would be V plus will increase. Oh, now can fight liao. Just now V plus was 1 volt. Cannot win the V minus 2.5 volt. But now V plus is going to increase. So when V plus increases until it is larger than 2.5 volt, the output will flip from positive to negative, from negative to positive. And if the output flip, then the different LED will light up. Okay, so V plus increase until V plus is greater than 2.5 volt, which is your V minus. Okay, and when that happens, V out is equal to positive 9 volt because your V plus is greater. Plus is greater. Okay, and also because of this, the red LED will light up. Two marks, that means, do I need to write the whole thing? Kinda, but not really. Very pain. Because you already analyzed the whole circuit, so they can ask you wherever also, you should be able to explain. You just have to make sure explanation is more thorough. Okay. Okay, so first things first, the changes in resistance. Okay, so the resistance of the LDR is greater in darkness. Okay? So because of this, you can say that this increases the non-inverting input V plus. When the non-inverting input exceeds or is greater than the inverting input, or you could say when it exceeds 2.5 volt, V out is positive 9 volt, red LED. Red LED emits light. Green LED, because you say an effect on the LEDs, you know, so you also have to tell them that green LED will turn off. Don't forget. So red LED emits light, green LED does not emit light. Okay, where is the mark? Resistance greater, increase V plus, 1 mark. So you explain the effect of LDR in darkness on the input of the op-amp. Number 2, talk about the outcome. Okay, so the output will be 9 volt, and then this whole red will emit, green will turn off, does not emit light. The reason why I didn't say on or off is because I'm copying back their sentence, which is generally a good rule of thumb to do, because the mark scheme will mimic the question. So if you want your answer to load as much as the mark scheme as possible, you will do that lah. Okay. So the second mark is when you say that when the V out will be positive 9 volt because your V plus increase. So your red LED will emit light and your green LED doesn't emit light. So what happened to the red LED and what happened to the green LED? This is 1 mark. Okay. So this is an example of a comparator circuit. Oftentimes you are asked to analyze the circuit that is given to you. And then from that analysis, you will be required to decide, oh, if I change this, if I connect this and that, what will happen to the output? And based on what is happening to the output, whether the output, whether the output is equal to the supply, whether the output is positive or negative, we will get we will get different kind of responses lah. Maybe your LED will turn on, maybe your LED will turn off, or maybe some relay switch will turn on, turn off. So these are all in the remaining examples, and this is all in this particular video. Okay, I'm fixing that. V out will be equal to V supply, but what we care about is the output. All right, so that's it for the comparator. Please try some questions. I will see you in the example video if you need them, or try out those questions first. All right, that's all for now. Take care. Bye-bye.